All right, hello. This room really seems to call for a chalk talk, so here we go. So let's see. So this is joint work that I'm presenting with Ibrahim Isa, who's a PhD student I'm working with, and Sudeep Kamath, who's a postdoc at Princeton. Can you see okay when I write? Yeah, okay. All right. So we're looking at a question that, that I think exists at the nexus of information theory in computation, which is the following. So suppose we're given a joint PMF between x and y. Okay. And here's the question. How much information does y leak about x? Maybe I should put leak in sort of scare quotes. Okay, so I mean leak in sort of a side channel sense. So the application that we started with actually was, suppose I log in to a computer at server at my home institution using the SSH protocol. Okay, once I log in, every time I hit a key, it sends a packet, right? So in fact, to render the letter on the screen, it actually has to get a response from the server, right? So every time I hit a key, it's going to send a packet out. All right, so the timing of the packets is highly correlated with the timing of my keystrokes. And so if I type something like my password, okay, then the timing of the packets, which are easy to pick up with a radio sniffer, will leak information about what my password is. Okay, and this leakage has been studied. It's not insubstantial. I mean, you can't determine the password completely from the timing, obviously, but it leaks quite a bit of information. Okay, so if you want to design a system to sort of mitigate this, like you want to put something in the OS of the laptop that will sort of randomly delay packets a little bit as they're sent out to try to minimize this, then the problem you're confronted with is, well, how do you measure how well you're doing? Okay, how do you measure how much information is being leaked about either the original packet timing or my password in the delayed packet timings? Okay, how do you quantify this? Okay, so that's one application. That's one we had in mind. It comes up lots of other places. For instance, if you look at the Shannon cipher system, okay, so you have, let's say Alice and Bob again, and Alice has a message that she's going to send over a rate-limited link to Bob, and Bob wants to recover the message, and there's a key, secret key that they both share, and Eve observes the public message and not the key, and you want to communicate the message to Bob and have Eve kind of learn as little as possible about the message. Okay, so if the key rate is high enough, then you can ensure that the broadcasted message is completely independent of the broadcasted part is completely independent of the message, so Eve really gets nothing. If you're not in that regime, though, then you're leaking something. You can ask, well, how do you design this thing to minimize the amount of leakage? But then you got to quantify what does leakage mean in this case. How do you measure it? Okay, so that's really the problem. Okay, so let's try that. Okay, so the various metrics people have employed, I guess it goes all the way up. Okay, there are various metrics people have employed, and there are metrics in the information theory literature, there are metrics in the CS literature. Let me start with the information theory literature. So metrics in the IT literature. So all these would be, in some way or another, like an answer to that question. Okay, so the first one, the obvious one that comes to mind would be mutual information. So just look at mutual information, X, Y. Okay, so what's wrong with that? Okay, I get that question whenever I tell people about this. Why don't you just use mutual information? Right? It's a very natural thing. I think sometimes there's sort of an undercurrent to the question when I get it, which is mutual information was good enough for Shannon. Why is it not good enough for you? Okay, so Shannon himself proposed using mutual information, or equivalently the equivocation, which is just off by an additive constant from this, to measure secrecy in that scenario. The difficulty I have with this is that it's not operational. Okay, there's no operational justification for using mutual information. Okay, as an information theorist, I use this a lot. I use it a great deal in my professional life. It is usually the answer to the question. It's not the question itself. And here we'd be using it as the question itself. Okay, and if we have two different schemes for the laptop, and one gives rise to less mutual information, can you really say it's better? It's better in what sense? People might say, well, it leaks less information, but that's circular, right? I mean, you're just defining. Anyway. So that's one issue with that one. Okay, now you can maybe argue, well, okay, if x and y are both IID sequences, then you can look at typical sets, and conditional entropy would tell you the size of some conditionally typical set. And so if Eve is trying to guess the value of x, then the conditional entropy would tell you roughly how many guesses it takes to find the true value of x, right? Maybe you can kind of justify it that way. But there's a very short but very important paper by Massey, an ISAT paper from some years ago that shows that entropy and guessing are not, maybe in certain controlled situations they're kind of related, but in general they're different things. So you can't really use this as a good proxy for guessing. All right, so option number 2 is like, well, if this is not capturing guessing, let's just capture guessing, right? So guesswork, as it's sometimes called. Okay, so you might, for instance, let n, capital N, be the number of guesses to guess x correctly from y. Okay, so you can imagine Eve, making just a large number of guesses, or keeps guessing until she guesses the correct x, and then you can look at some power or some moment of n, right? So like how many guesses does it take to guess x? Okay, this is operational. It's good. The one difficulty with this, however, is that in many sort of naturally occurring configurations, n, so especially when x and y are sequences, okay, and then n is growing exponentially, okay, and so you're looking at, n itself is exponential, and you're looking at this kind of scaled version of it. It can easily happen that the typical and expected behavior for n is different. Okay, so in fact, it can easily happen. I can show you very natural situations where if you apply this metric, the optimum scheme has the property that with probability near 1, you reveal x exactly, and there's some exponentially small probability that is exponentially difficult to guess x from y, and so this expectation gets dominated by that very rare event, and this metric says it's secure. Okay, when in fact no reasonable person would ever call this secure. With high probability, you're revealing x in its entirety. Okay, so the expected behavior and typical behavior can diverge for this metric. Okay. Okay, number 3, expected distortion. Okay, so instead of saying you get many guesses, you just say Eve makes one guess, and you have a distortion measure. And you look at the expected distortion between her one reconstruction, and the true source. This is sort of plagued by a similar problem as 2, wherein systems that are not at all secure can get sort of artificially labeled as secure. So if x, for instance, was an IID uniform binary string, okay, and y was of the form that when you see y, there are 2 possibilities for x, like one string and its complement, like all zeros and all ones, okay? Then the distortion that Eve would have with a single guess would be half the bits, which is like the maximum possible. So the metric says this is as good as y being independent of x, when of course y is not at all independent of x, right? You've revealed everything but 1 bit, essentially. Like once you know 1 bit of x, then you know everything, right? So that's not really a good way of doing it either. There's a patch for this. So expected distortion with feed forward. I don't know if I really want to get into what exactly feed forward is, but for people who know it, you can probably imagine how this would work from 3. It does fix the problem I just described, okay, that kind of bit scenario problem doesn't arise. But I guess I'll say you kind of lose this sort of strong operational motivation for it. Like this feed forward problem doesn't necessarily coincide to kind of realistic eavesdroppers who are trying to guess what you're trying to hide, okay? So, and there are others. I'm not going to go through This is just the IT literature. We haven't gotten to CS yet, but just in the IT literature, there are others. But I'll say at the end of the day, we were not able to find kind of one metric that we felt was both operationally motivated, operationally justified, and did not have these sort of obvious counterexamples where it labeled a system that's insecure as secure, okay? So at this point, we decided to make up our own. In hindsight, we should have consulted the CS literature first, okay? We didn't do that. We just sort of, given this, we sort of created our own. So let me describe what we did, and then I'll show you how it relates to the metrics that are in the CS literature, okay? So our metric we call maximal leakage. Okay, so definition. Okay, so the maximal leakage, I'll say from X to Y, it's defined as follows. I'm going to write it like this. So L for leakage, and then I'll write it like this. It's like the amount of information from X that's sort of seeping into Y, leaking into Y. All right. So here's the key equation. There are like two key equations in this talk. So this would be the first one right here. All right, so here's the motivation. So if you think about the laptop example, I'm going to design a device that takes the packet timings and sort of blurs them a little bit before they get sent out, right? The packet timings themselves aren't really that important to me. I don't know what that was my mic, I'm sorry. The packet timings themselves are not especially important to me. It's more the, is that better? Okay, I can lower my voice too. Am I shouting? The packet timings themselves are not especially important to me. It's more the password, right? Like, I mean, there are things I'm typing that I'm trying to hide, and I'm trying to blur the packet timings to hide those things, right? And if you think about the password situation, the adversary has a mechanism by which he or she can test a candidate password, right? He or she can try to log in as me, and if their guess for the password is correct, then they'll get in, okay? And I'd like to minimize the chance that they're able to log in as me by guessing my password by extracting information from this packet timing. Okay, so we're going to try to kind of capture all of that, what I just said, in one equation. All right, so let's consider a random variable u, which satisfies this Markov chain condition. So given x, so x and y are given, okay? Consider a u that's coupled with x and y so that u and y are conditionally dependent given x. Okay, this is like my password. These are the true packet timings as they emerge, from the OS. These are the blurred packet timings that my device would create. All right. Now, I can consider the chance that the eavesdropper can guess my password having seen y. So that would be supremum over all u hats that hang off y like this, of the chance that u is equal to u hat. It's the chance the eavesdropper can guess the password having seen y, right? I can compare that to the chance the eavesdropper can guess u having seen nothing. I'll assume u is a finite valued, discrete random variable here. So just max over u, p sub u of u, like that. So there's the multiplicative increase in seeing y, right? I'll take log of that. Now it's in bits for log base 2. All right, now the thing is, in practice, we don't necessarily know what we're trying to hide or how it's correlated with the packet timings. So I don't exactly know what u is and how it's related to x and so on. So I'll take supremum over all such u. That's the metric. Okay? Okay. It's not clear when I write this down that this is computable. Right? If I don't impose a cardinality bound on u, if we said u had to be binary, for instance, okay, then you could just search that inner supremum there. You could search over all possible conditional distributions from u to x and so on. If you don't impose a cardinality bound on u, then it's not clear a priori that there's an algorithm that will compute this, right?
Can you just repeat what's the motivation for the transformation ratio?
So there's the so certainly the the eavesdropper can just try to guess my password blindly, right, with no information at all, and that's the denominator. Okay. By virtue of the eavesdropper eavesdropping on my packets, the eavesdropper effectively observes what I call y here, and can then try to use that information to also guess the password. And it's probably going to be more likely to be correct because the eavesdropper has more information. Okay? And I'm judging how good my scheme is by how much the latter probability exceeds the former probability. So the more information I give away about x and y, the more of an increase you'll get in guessing u from nothing versus guessing y. I don't think I've convinced him, but let me make one aside, and then we can, while you think, I'll write one thing down, we can come back. So I'll just point out one thing that kind of inspired this, this definition is you can compare it to the strong data processing inequality, strong data processing constant. So of course, you know if you have a Markov chain like this, okay, then it's kind of well known that the mutual information between u and x has to be less than or equal to, sorry, greater than or equal to the mutual information between u and y, okay? And for a given joint distribution between x and y, okay, you can look at how large this ratio can be. Take the smaller one divided by the bigger one, like that. So take out supreme over all u. This is something that's called S star of x and y. Okay, so there's some connection here. Obviously, there's not a direct one-to-one relation, obviously, but this is sort of what inspired that, along with the operational interpretation. All right, Aslan, Rajesh, yes.
So why did you take the supremum of the ratio?
You mean why the log?
No, the log alone. You have a supremum in the numerator and a max in the denominator.
Yeah.
Is there a motivation for doing this sort of comparing it with the best max in the denominator?
What would be alternative? What would you put in the denominator?
Over u, x, y, you had Markov chain. Probability of u equal to u hat divided by probability of u.
It's the max of the max is like one max of the ratio.
Max of the ratio.
I mean,
I don't understand. Yeah. I mean, I want the probability that you're able to guess u correctly with nothing, and the probability that you're able to guess u correctly with y. And I compare those two.
They say take the max over this overall u, not of the ratio, not two different maxes, one for the denominator and one for the denominator.
Because I want to weigh those u which are less likely somehow.
So what max do you move? Do you move one?
Move the PU of u inside the numerator. Move the max.
But that's a function of u. So if you move the u, I don't know if I can move this down if there's a pointer or something. I mean, this is a function of u here. So when you take max over u, that's a constant. It just depends on the distribution that you pick here.
Supremum is over u as well.
Oh, you want to move this supremum out here and then take it over this one and that little u. Well, these are decoupled, though. So, I mean, you would just get, I mean, the two supremums just separate, right? Unless I'm missing something, it seems the same. OK, good. All right, not clear is computable. You can write this thing down. You can say, yes, it's operationally motivated, but if you can't compute it, what's the point? OK, in fact, so the reason it's not computable is we don't have a cardinality bound on u, right? And in fact, it appears that there is no cardinality bound on u as a function of the cardinalities on x and y. Okay, so for a given cardinality of x and y, you can construct examples where the PMF of x and y dictates a really big u has to be used, okay, which seems like bad news. But nonetheless, we can show that this thing satisfies a very simple formula. Okay, so here's the main theorem. Okay, so this is again with Ibrahim and Sudeep and myself. Okay, so we can show that so I'll just state this for the finite alphabet case. So if x and y, finite alphabet. Okay, then this leakage. Okay, it's a quantity that has a name already, so it's the Sibson mutual information of order infinity. Okay, so this is, I'll write it I infinity xy, okay, which is, let me write it up here. It's log, from that log there. And then you have sum over y, maximum over all x in the support of x of the conditional. Like that. In particular, it depends on p of x only through its support. Okay, it depends very crucially on py given x, okay, but the marginal of x only enters through its support. Yeah?
Will you give an operational meaning for this?
Sorry?
Will you give an operational meaning
For this?
for the leakage NX by your definition? Because I think you dismissed all of them saying some of them were not operational.
Yeah, sure. It is, ready? It is the multiplicative increase in the probability of guessing a secret u hidden behind x correctly, maximized over all such hidden secrets u. Log of that. I mean, all I've done is taken that equation and express it into words. But I mean, I argue this is operational. I mean, it's the probability of guessing the secret correctly under two different scenarios, and you're comparing the difference between them. Okay, which I mean, I agree. I just to be punchy, I agree. I was somewhat dismissive of these, but I mean, I don't know of a comparable thing for one, for instance. I mean, one I don't think that has even that. Yeah. Did you have a question?
So how does it compare to the mean entropy of x given?
What do you mean by min entropy?
The log of the maximal guessing conditional guessing probability.
The log of the, yeah, so actually we'll come back to that when we talk about the CS literature, which we may not have time to do. How much time do I have? 10 minutes. Okay, I was planning on proving the theorem. That will probably use the 10 minutes. I can also talk about connections, though. Would you rather do proof or rather do connections? Let's choose your own adventure. Connections? All right. Okay. So let me do. Let's do a couple of examples first. Set the stage for the connections. So let's suppose x is Bernoulli p, or p is not 0 and not 1. Y is x mod to some z. Z is Bernoulli q. Q is, I guess, could be 0, but no more than half. All right, so you take a bit, you pass it through a channel that gets flipped. Okay, so this you can get very easily from this formula. All right, it's just log of 2 times 1 minus q. Okay, in particular, if q is 0, then you're looking at the leakage from x to itself. Okay, and that is 1 bit, even if x is biased. Okay, so remember, it doesn't depend on the support. It doesn't depend on the distribution of x, only through its support. So any two Bernoullis, with different parameters, as long as they have the same support, you got to have the same leakage back to themselves, right? So. Okay, one more. So I did this I wrote this down, the theorem down in the discrete case. If x and y are jointly continuous, the definition still makes sense because you just force u to be discrete, so you can talk about guessing probabilities, but x and y can be whatever. The definition still makes sense. You prove a theorem similar to this, you just get integral We get a conditional density. Okay. So if you suppose X is Gaussian, and you observe it in the presence of Gaussian noise, your Z is independent of X. That's also the assumption here, which I guess I didn't write. Okay, I can then look at the leakage from X to Y. So take a Gaussian random variable, add Gaussian noise to it. How much do you leak? Infinity, actually. Okay, so it's not too hard to see because you're going to get an integral over y, and then you're going to get max over x, like this, right? But given any y, you can just choose the x that's equal to it, and then you got just the peak of the density of z right here. And so this integrand actually does not depend on y. So you integrate one constant over the whole real line, you get infinity. Okay? So adding noise is not a good idea, according to this metric. Okay? What is a good idea, it kind of depends on what you're trying to accomplish. We have no like utility function here. We're only talking about the privacy constraint. Okay, so we have looked at some problems like the Shannon cipher system, for instance, where we have kind of a utility constraint and a privacy constraint in tension. And we use our maximal leakage constraint. And I can say anecdotally, what we tend to find is that schemes that fare well under this metric are more quantization-based schemes. Because you take X and you quantize it and reveal that. That does much better than trying to just blur it by adding noise like this. Okay? All right, so now let's talk about connections. And I guess I got to figure out how to make these things come back down. Okay, so let's compare it against, so I mean, I've discussed IT metrics already. Let's talk about metrics from the CS literature, so metrics. Okay, so first one that comes to mind is differential privacy, right? Okay, so it's not. Yeah, I mean, just looking at the sort of most prominent differential privacy papers, it wasn't entirely clear to me what the metric was. I mean, the metric is that they use is sort of embedded with the database formulation, so it's not so easy to just pull out a metric and say this is the privacy metric in use. But I think if you try to force the matter by just sort of extracting a metric, then I'd argue what you get is the final, I'll call it differential privacy, or DP for differential privacy. And it's basically, it takes a premium over all y events A and all realizations for x, x1, x2, log, and you have a chance that y is in A, given x is x1. I have the chance that y is in A, given x equals x2. All right, so I might argue that's like effectively the leakage metric that's in use in differential privacy. Okay. So this is known to be like a strong metric, and that it tends to evaluate just big numbers. In particular, it's quite easy to show that it always upper bounds our metric, like so. Okay, that's maybe, I don't know if that's obvious or not, but I mean, you can just choose A to be a singleton, and then you have just statements about the conditional PMF, right? So the ratio of these two is upper bounded by the leakage, and so then if you go to our, the theorem is covered up in our thing, but you're taking the maximum over x of the PMF. That maximum can't really vary too much as you vary the x when this is true. So you just sort of plug this in, and that's that. This inequality can be very far from tight. In particular, if in my, it's a shame the third board didn't go up, that one's fixed, but if in the binary example where x and y are both bits, if y is equal to x, So the channel is noiseless, so just X gets copied through. Okay, our metric says you're leaking 1 bit of information. Differential privacy would say infinity. Okay, because you have, there are some XY combinations, they have different support, right? So some XY combinations have positive probability for one X and then 0 probability for another, right? So you get infinity. So it would say you're leaking an infinite amount of information in that case. So it's very conservative, clearly. And I haven't really worked in differential privacy too much myself. I've been talking to people who do work in it, and my understanding, if people here are experts in this, you can tell me your experience. But talking to people, my understanding is that many people who work in this view it as perhaps an overly conservative metric. I mean, it's so conservative, in fact, that it's not necessarily always useful. Whereas this metric is also, it's operationally justified and it tends to value something smaller. So perhaps it would be a suitable replacement in some cases. Two, so there's this notion of cryptographic advantage. This definition exists in a bunch of different forms. Okay, in some forms of it, people constrain the adversary to be computationally bounded. So the adversary can only do like polynomial time algorithms and so on. I'm going to sort of cherry pick the version of it I found in the literature that's most similar to mine to allow easy comparison. So that one would be the following. So we'll compare it to ours. So again, it takes a primum over all u. Okay, but now u is required to be a deterministic function of x. So u equals f of x for some f. Okay, and you look at the difference rather than the ratio. What's the chance you can guess it armed with y minus the chance you can guess it without. So you can put absolute value if you want, but this one's going to be bigger than that one, so it's OK. All right. OK, so two differences. One is you require u to be a deterministic function of x. The other is you've got difference versus ratio. Okay. I personally am more comfortable with the ratio. These probabilities, these guessing probabilities might be very small a priori, and you could have a scheme that takes what was a very small probability and makes it quite a bit bigger, although still small in the absolute sense. And then when you look at these differences, it might be hard to perceive that, whereas the multiplicative gain is perhaps more meaningful in that regime. With regard to this restriction, that u be deterministic, I don't know about this setup, but in our setup, you can show it does make a difference. So if I add the constraint that u must be deterministic to that supremum, okay, it changes the answer. In fact, you can construct xy distributions so that if you require u to be deterministic, the leakage is 0. But if u can be random, then it's not. Okay. And then, and in fact, there are many other properties that we've shown about this. I didn't, since I skipped the proof, I also skipped the properties. But you can show this leakage is 0 if and only if x and y are independent. You can show it's greater than or equal to mutual information always. You can show it's additive over independent components. Okay, so if x1, x2, you have x1, x2, and y1, y2. If the ones are independent of the 2's, the leakage from x1, x2 to y1, y2 is just the sum over the leakage over component 1 and component 2. Okay. You can prove a data processing inequality, for instance. There are a lot of things you can prove about it. I have one more CS metric to discuss. Do I have time for one more? OK. What board is this? This is 1, right? I don't know of one. No. Okay, so third and last metric I'll talk about from the CS literature. Okay, okay? It's actually called maximal leakage, okay? And this is not entirely a coincidence. So this is due to various people. Okay, so Braun, Chatziko-Kolakis, Palamidesi. Okay, that's one paper, and then Koff and Smith. All right, so it's the same name as ours, okay? And the history is that we developed ours independently, and then once we had ours, we found this. Their operational definition is slightly different from ours, okay, but it evaluates to the same Sibson mutual information, okay? And this might actually answer your question about the guessing. Okay, so their metric works as follows. I'll just call it L prime. Okay, so again, there are two differences. Like with the advantage, the differences are different though. They assume there's no u, you're trying to guess x itself. Okay, but then they take the worst case marginal over x. Okay, so x is not given as part of the problem for them. The py given x is given, and you consider the worst case marginal for x when you're trying to guess x. Okay, so this would be, so you take the worst case PMF over x, okay, and then you have the same log ratio that's the chance you can guess x armed with y, divided by just the chance you can guess x armed with nothing. Okay. All right, and what these groups have shown is that this evaluates to the same Sibson mutual information, which I called, I think, I infinity. Okay, so it gets the same formula. Okay, so we had actually tentatively settled on calling our metric maximal leakage. Like that was sort of our working name for it. We were about 90% sure we wanted to use that. And then we found this. I was like, that seals it. Okay. I mean, there's basically a different metric that evaluates to exactly the same formula. It's called maximal leakage. So we got to stick with that. Okay, so we use the same name. Okay. Does this answer your question about the relation to? Okay, maybe not. All right. How much time do I have? -2. All right. I won't write anything. Let me just go to -3. So let's see. We've looked at various extensions of this. In particular, like in the password example, the eavesdropper doesn't just get one shot, right? The eavesdropper can maybe try your password a few times before getting locked out. So you can reformulate the problem where in both the numerator and the denominator, you get k guesses. And what's the advantage or what's the improvement in observing y when you get k guesses? Okay, it evaluates to exactly the same formula. It's again Sibson mutual information. It doesn't change the answer. Moreover, in some cases, the u you're trying to hide is not a discrete quantity that's guessable. Like people are into location privacy now, for instance, right? So how do I send signals to, how does my phone send signals to the base station in a way that, follow the protocol and so on, but makes it hard to figure out where I am? Okay, so my location is not necessarily a discrete random variable you can guess like this. So we've considered another formulation where it's like a distortion type formulation where the eavesdropper is trying to guess u to within a distortion ball. Okay, again, it gives us exactly the same answer. Okay, you get Sibson mutual information again. Okay, so it seems very robust, which is good. So that's it. So we have this metric. It is operationally motivated. It's quite simple, which I think is important for this. And it's less conservative than differential privacy. So hopefully it will be useful to some people. All right, thank you. Okay.
The reason I asked the question about bringing the U up is actually related to trying to see if there is some connection to the guessing problem. So it looks like what you have here is the top guess. So in the guessing problem, you're essentially one of the early motivations or early information theory metrics you gave was expected number of guesses.
Right.
So if instead of looking at the expected number of guesses, you just have one guess, which is the top item in the list, you have to get it correct. What's the probability of getting that right?
Yes.
So perhaps I think this is related to getting the top item right. But I don't know how to connect it up. So maybe there is an operational connection via that viewing at the top of the list rather than at the bottom. That focuses on the bottom, the tails, because you have to do well on things which are rare.
Yes.
But you should do well on things which are frequent. So that's...
I agree with you. And in fact, we did that first. So we had an allergen paper in the fall. That sort of laid out these issues with these metrics and then proposed a formulation that was essentially that. The only difference was we allowed a distortion ball around X. So, I mean, you choose the distortion ball and then the eavesdropper is trying to guess X within the distortion ball. And the distortion could be 0, in which case you're trying to guess X exactly. The limitation with that formulation that we felt existed was that in some situations it's not really X itself you're trying to guess. Like in this case, it's, the packet timings themselves, who cares about the packet timings? But the packet timings are correlated with something behind the scenes that we do want to hide, that we do want to prevent the eavesdropper from guessing. And that could be related to X in a very complicated way. We might be trying to guess or hide many things simultaneously. So rather than just trying to make it hard for the adversary to guess X, we said we want to make it hard for the adversary to guess all hidden U's uniformly in some sense. And that's what gave rise to this.
So my question is somewhat related to the previous one. I was just wondering, because at the denominator you have, so it corresponds to the best guessing without side information, and the denominator is the best guessing with side information.
Right.
But the numerator is expectation, whereas in the denominator is the worst case. So why don't you have also a max inside within the soup? So you would have the soup of x, y, soup of u, x, y, u hat, and max over u. Yes, inside exactly there. You put the max over u. Yes.
Over little u, realization?
Over little u's, yes.
Over little u, okay.
Yes.
And then what?
That's it. Because then it's so this is because the previous case. I mean, again, the denominator is the best corresponds to the best guessing without side information.
Right.
The denominator is the best guessing, but it's average over the y's.
This
right?
one?
Yes, it's averaged, right? So it's average over the y's, right?
It's averaged over the y, certainly.
It's u hat of y, right? So it's this.
Yes.
So it's expectation of p of u hat equal u given y.
Yeah.
You take expectation.
It's expectation over x and u as well.
Yes.
So it's expectation over all of that in some sense.
Right.
Yes. This is expectation over u, I'd argue.
Right. So why do you have? I mean, again, so you have expectation on top, and you have max on the denominator.
No, I mean this is really the this is like maximum over all estimators. So you can write supremum if you want. Supreme over all estimators.
Yes.
It's really that. I mean, I write it differently, but it's just they're sort of the same thing. It's just here u hat depends on y. Here u hat is deterministic. I mean, it depends on nothing. Like that.
Maybe this is a little clearer.
Is it? Okay.
Because now you're using side information.
Yeah, you use side information here and not here.
Yes.
But in both cases, the supremum in both cases is really capturing like the best estimator given the information available. And in both cases, you're averaging over u and the estimator and all the other variables and so on. I mean, here y plays no role, so I mean, you don't have to explicitly average over it, but you can think of it as an average over y if you want. Yeah.
Yeah, so usually for these quantities, it might be useful to smooth it in the sense that there might be some event that happens with probability epsilon, and epsilon you think of it as small in the sense that you allow it as an error probability, but it's also large in the sense that it doesn't grow with system size. So have you looked at smoothed versions of these quantities?
No. In fact, I'm not entirely sure what a smoothed version means in this case. I can, however, recognize the need for something like that because I view the data of the problem here as the joint pxy. The metric is not continuous in pxy, however, in that if a particular x symbol has positive probability, then that row of the stochastic matrix takes you from x to y is relevant in this maximum and so on. As soon as that thing has zero probability, then it's gone, right?
Yes.
So that is potentially a problem. In particular, I'm not sure you could learn this thing from data. I mean, if you observe x, y, streams, it seems like that would be kind of problematic in terms of estimation. So perhaps some sort of tweaked version is called for. On the other hand, I'll say, in practice, you don't really even know P of X well. This would be the actual packet timing distribution, right? It might be hard to infer that in reality. So you might just assume X is full support. And then the distribution of X doesn't really matter. It doesn't enter the formula at all. And really only Py given X matters, but that's really the thing, at least in the application I have in mind, is the thing I design, right? So I have to try to learn that from data. I get to pick that. So it's okay if it depends on that thing a lot.
Okay, yes.
Yeah.